Today I'm going to talk about NeRF-VAE, a geometry-aware 3D scene generative model, work done by Adam Kosiorek, Heike Strutman, and others from DeepMind. And on a high level, this paper is about basically integrating VAE with something that if you want to use VAE to reproduce a scene that come from a 3D world, like say some scenes, like in this case, is going to give some kind of geometric prior to the VAE, to the decoder and encoder, right? Because normally in a normal VAE, there's no geometric prior, right? The geometry, so things like perspective and all that, either the decoder and the encoder, they both have to learn how to render kind of scenes. And if there's anything like a latent variable that represents something like, I don't know, like position of an object, or anything like that, there's going to be the encoder that has to translate the position of the object in a geometrically meaningful way into something that makes sense geometrically, right? So here I try to use some some techniques coming from NeRF, a previous paper called Neural Radiance of Fields, to exploit to give some geometric awareness to the variational encoder. And so what they do here is they have a bunch of scenes, basically like this, where you have something like an arena. So these are synthetic data, and like they have something like some kind of game arena where they have objects that they spawn in this arena, and they have like different colors or different shapes and different positions, right? So each configuration of objects and position corresponds to a different scene, and you want to give a set of these images together with the position and the orientation of the camera that took that image, and from that set of images, an encoder is gonna extract some latent variables that represent that scene, right? So those could be, so if they were interpretable, those would be the color of the objects and the position of the objects or something like that. And then once you have the encoder, you're gonna create the decoder is gonna create basically a 3D representation of this scene, so that now you can give it any other orientation and position of a camera, and it was gonna give you back the position, so the image resulting from having the camera in that position and that orientation. So what image would result from would have been taken from that camera. So to explain this, I think it's better to start with this NeRF paper. This is called Representation Scene and Neural Radiance Fields for View Synthesis. And what it does, the problem that this paper tries to solve. So later we could trying to combine this with VAE, but first I think it's useful to understand this paper if you don't already. And the problem they're trying to solve here is that if you have a bunch of input images of an object from different views and different orientation, say taking it in this manner where you you kind of surround, you go around the object in a fixed intervals, you take a picture of that object. The problem you want to solve now is we want to build a 3D representation of that object. So that now I can take a different orientation and a different position of the camera, and I can still have an image that makes sense of that object. And the way this is done is with this radiance fields is by doing something like by basically differentiating radiance fields, or ray tracing, I think it's called also. Where you would have so let's say you have the image from here, right? Or better said, you start from the opposite side. So let's say you already have the model, right? And you want to get an image. You have the 3D model, and you want to get an image by knowing that the camera is in this position with this direction. So what you do is like you have a ray, and the ray pierces through the image you want to create in a particular point, and that you now have the problem of determining what is the color of the pixel here where the rays goes through. And that pixel is going to be the value or the color of that pixel is going to depend on all the voxels that are intersected by this ray. So what a voxel is like a generalization of a pixel in 3D space. It's like a unit of volume, right? So we discretize the space here in this cube, so that we have we have a grid, a 3D grid of volumes, of little unit volumes. We call it voxel, and we look at all the voxels that are intersected here by this ray, and depending on where this ray is, so what this voxel is it's going to have a different influence on the value of the pixel here. So, for instance, if it is each of these pixels here is going to have a color, and it's going to have a density, right? So pixels that have a higher density are going to play a bigger role in determining the color here, and pixels that have lower density are going to play like a less of a role, right? And also, like if there's a lot of pixels before, so let's say you're trying to determine the let me see. Okay, you're trying to determine the color of this pixel here, and you're like looking at this pixel here. You're considering what is the weight of this pixel in determining the voxel in determining the value of the pixel here. There's a lot of pixel before this one, and if their density is the sum of their density is very high, this one is gonna play less of a role in determining the value of the pixel here, right? So this is like a kind of a general idea, I guess. So there's an equation that like determines the color. So this is like determines the color of one. We consider one ray, and we're looking what is the color. C of R is going to be what is the color of the pixel intersecting that ray. So the pixel where the image here or canvas intersects the ray. Okay. So that value is going to be the integral or the weighted. So the weighting. This term here is kind of a weighting of all the colors that are like the rays intersect. So here you're gonna go at different coordinates that are determined by the ray. The ray is this thing that like is determined by direction, the starting point, and as t goes, as t increases, we follow its direction, right? And the color is of all the voxels are intersected here, depending on where t, what is the value of t, are going to be less or more important depending on this t, and sigma. Sigma is the density of the thing that we're looking at, of the voxel. Is the density of the voxel that we're looking at this right now in an integral, right? So where we are in what is the value of r of t? So where is the ray right now for a specific t, for a specific value of t, right? And so what is its density? And this other thing here, t, is going to be something that the probability that the ray travels from Tn to T without hitting any other particle. So probability that basically it travels from here to whatever thing that we're considering now in our integral without hitting any other particle in a way. So if it's something deep inside the volume of the toy object here, it's gonna be a bunch of particles that have very high density. So the probability of the ray hitting any other particle or any other voxel before it gets to this particular voxel is going to be very, very high. So we're going to consider it less. So the weighting of that color is going to be less, right? So this is t, and you can see that it's like the exponential of a sum of all the density that go to the from the beginning to the voxel being considered right now. So this thing is then discretized. The discretized version is this one, and this is also differentiable. So you can go and sample. So you can go and if you're given a specific position and orientation of a camera, you can start like shooting these rays and sampling all the different voxels and render it. And what you're trying to learn is a function that, given the coordinates x, y, z in this 3D space of each voxel, and phi and a direction in 3D space, so given by two angles, it gives you back an RGB, so the color, RGB color, and the density of that particular voxels. In that way, you can apply this simple function to all the voxels that are hit by some ray at some point in the rendering, and get a value of the RGB and the density, which is all you need really to render your image. And since you can propagate to the through the ray tracing algorithm, you can basically start from so render this thing, right? Have something, have some network here that renders that determines the RGB, and then like because you know these images, right? You can optimize this through the through this ray tracing algorithm, which is differentiable, so that you optimize this to give you all to reconstruct the images from each of the camera, right? Because you have those images, and so you have a reconstruction loss, and you use that to have to basically build this model. And this model is going to also be very kind of efficient in memory or from a memory point of view, because you're not going to try to like kind of go and pick a value for each of the pixel. You have a function. So the things that you're going to learn on the parameters of the network, not a value for each of the pixel, right? So it's kind of compress the image, right, so the 3D model. We don't have to specify the value for each of the pixel, but you only specify a function that you then apply to the voxels, to the position and orientation of the different voxels, and to get the final thing. So that to get the final 3D model, basically. And one thing that is important to notice is like the positional encoding. To make this thing work, they noticed that it didn't work so well if they only give to the network the X, Y, Z, Phi, and theta, like just like that, the values. And that is something to do with the same fact, the same reason why in Transformer, when they're giving like a specific entity into a sequence, or a specific word into a sentence, they don't just give the number, like this was a second word or a third word or so forth, but they encode it using a bunch of sine and cosine waves, and that makes it more readable, more interpretable by the network. It is easier for the network to learn when data is given in this way, and this has been observed in the Transformer and in other architecture as well. So they do this thing. Also note that whereas the color is different, so for each orientation the color changes, right? So it matters. A certain voxel, the same voxel, can have a color if looked by looked from a specific position, specific direction, and another color if looked by another position, up another direction. And this is done because, yeah, so they made it so that the density is only dependent on X, Y, Z, and the color is dependent on X, Y, Z, and Phi and theta. Okay. Another thing that they do is like, so here a problem that you have is that you're sampling like things on this array. So for each array that you're considering, you're sampling like voxels on that array. And so for some of those voxels, they're not going to matter much in the final rendering of the scene, right? Because maybe think of this toy like in the middle of the volume of that toy. You could have a pink pixel, red pixel, whatever you want, and it's going to play absolutely no role in determining the final rendering, right? So depending on, and they also observe that this thing, this equation here that determines the color, can be also rewritten as let's see, in this way, where you have like the colors, each of the colors for each of the voxel on the array, and you have a specific weighting, and the weighting determines this probability of the ray being deflected by some other thing, and also from the from this, which is the basically a function of the density of that particular voxel. So they can use this weighing instead of for not only just for rendering, but also for sampling. So they're going to have a network, two networks. They basically learn the same thing. They both optimize to minimize the reconstruction loss. But the first network is going to, its weight, so this thing, they completely depend, so this thing here, they completely depend on the density, which is output of the first network. And these weights are going to be then used to sample to determine like basically a distribution over all of the. So here they're normalized to give a distribution where you're gonna sample from, which you're gonna sample from. So for array, you're gonna sample on this distribution instead of sampling uniformly. You're gonna sample from that distribution, which already tells you which are more important or which are less important, but which pixels are more important, which voxels are less important. So this is not a trick that they used. So now that we talked a little bit about the NeRF paper, let's go back to the VAE. So once we understand this, the only difference here is that this is the same thing as the function that we talked about before. This g of theta is the same thing as this function that takes in the position and the orientation and spits out the color and the density. Only here is conditioned on latent variable z, and so that means that for the training model such that given a set of context views, so maybe 3-4 views of a new scene, and you know also the related orientation and position of the camera in that case, you have something like an encoder here, which is gonna find out what are the latent variables that would result in that scene, and those latent variables then you have your function, the normal function you would have had in a NeRF paper, you have the condition on z, right? And that creates a function that determines the color and density, and then you give it a different so that determines completely your 3D model, which you can give then your different position or different orientation to, and that's going to give you a distribution over over images, basically distribution over final images, the render image, and then you try to optimize or maximize the expectation of the true image, of the true the one that you know. So the reconstruction is a kind of minimize the reconstruction error. You maximize the probability of the image, the true image being the one that is outputted by the network. So this is what I was saying. Like the loss is like this is the reconstruction error, and this is the Kyle divergent loss, which is with the prior here, which is normal in variational autoencoders. And so yes, another thing that they talk about here is they still have the positional encodings like as in the NeRF paper, but here they change a little bit the architecture because they had to condition on this latent variable z. They have an intention mechanism, and they have multiple kind of layers or a sequence of attentional layers, and to each one of these layers they basically split the latent vector in n chunks, and to each level they give you only a chunk. So each level gets to use this or gets to integrate information from the latent variable with the information coming from the previous layer of the attentional model. So here you can say that with that the positional information is encoded. It's what determines the query, and z is what determines the thing being queried, which makes sense because this determines what the scene is, and then where you go from position to position, you're gonna ask the question, okay, what is the scene in this particular position, and the information about the scene is encoded in z, so that makes sense. So yeah, and here also they have that the information about the orientation is and the information about the position both determine the RGB colors. So here this is concatenated. The information from here is concatenated with whatever is coming out of here. Whereas for the density, it only depends on the position. And finally they have something. So you can say that here is not just the encoder. They have something more, something else going on here. And so what they're doing here is this amortized inference, or iterative amortized inference. And what is useful for, or why they do this, is because thing that so normally here you're doing something like in normal NeRF, you would, for each scene, you would completely use gradient descent to learn a different function, a different model for that scene, right? That means that all the information that before were encoded in the parameters of this function, of this multi-layer perceptron that they use in NeRF, you're gonna have the same information now is gonna be compressed in this latent variable z, and the whole process that you went through to arrive to that z, which was gradient descent in that case, is going to be equivalent to just the encoder. So in one step of the encoder, you expect to get a z for the encoder to understand that like that scene can be represented as a set of variables or a vector of latent variable z, which is, I mean, you can make an assumption that the latent that the encoder is powerful enough to do this, but it doesn't have. I mean, it could not be the case, and it has to be all of it in one iteration. So to kind of make it more, to make it more powerful, so they can make more, so it can iterate too, like gradient descent does, although less updates. They use this thing, which basically is going to compute. It's going to draw, so it's going to draw some, you're going to have an encoder parameterized by lambda, and you're going to have the context. This is information about the image and the position from which this image was taken, right? And you initialize lambda with something like a 0 vector, here they also propose, and you're going to draw some z, and you're going to compute with that z, you're going to compute the loss function and everything. Then you're going to take the gradient of this and also the an encoding of the context vector, and you're gonna give it to a function. This is like an LSTM, right? So the LSTM is going to take the update. So instead of having the update it's gonna take the gradient. But like the key thing here is that they're not doing the update like with gradient descent, but they're having like the learning to optimize basically, right? So they're learning an update rule, and the update rule is parameterized by an LSTM, and the LSTM takes in like I think there was a paper called like learn to optimize or something like that that did something on along this line. But here you take the gradient, you take an encoding of the context vector, and you decide what you perform an update rule on lambda, and the update rule is learned while you learn everything else also, right? It's kind of meta learned. So that update function, instead of being just gradient descent, it could be some kind of update rule that is very specific to the scene that you're considering, right? So to this scene you're considering. So for that reason, you expect it to be much faster than gradient descent. So it's gonna try to change or like basically adapt the lambda parameters of the encoder to the scene that you're considering right now, very quickly in a bunch of updates. That's what I got of their use of this update thing of this iterative amortized inference. But they also run some experiments where they don't have that at all, where they don't change. Basically, there's for a different scene, they basically relearn this with this learn update rule that relearn these parameters lambda. There's also like a version in which they just fix it, like a normal variational autoencoder, where you just this one is just given to to this, and so you don't have this updating of lambda when each scene is proposed, basically. So then let's go to the experiments. The experiments here, they show that the NeRF is much so it can perform much better, meaning the reconstruction error is much lower, even with drastically less kind of context. So you're given a bunch of images about a scene, and then you're asked to reconstruct a new the image from the new position and orientation, and it performs much better in reconstructing the images than than the normal NeRF. Keeping in mind that here they're not learning, they're not doing gradient descent. Here it's not like a new model for each of the scenes, right? Where here is a completely new model for each. Trained from scratch for NeRF is a completely new model for each of the scenes. And also they need much more images, context images, to train the model. And they perform much worse. Which is to also, it's not completely surprising, because like also here, all the experiments they do, they always like take, so the different scenes are always taken from a kind of like a general environment, right? So in this case, it's going to be this kind of environment, and different scenes are going to just be different configuration of objects and with colors and shapes and whatnot, but they're always going to be the same kind of thing, right? The same kind of variation on the same theme. I doubt that this thing would work just as well if you just gave him like random images from like from real images and not synthetic images, because some of the information here is encoded in the, so that here that doesn't include all the information about the model or about the scene. It includes, because some information are repeated, right, across different scenes. So those information are repeated. For instance, the wall here, when it looks like a wall, or the sky, or the fact that there is like a floor, and all these things are encoded still in the decoder and encoder model. It's all these things that vary that are encoded in the latent variable. This is normal, like is true of all variational encoders, and so it's not surprising that as long as these things are, so all these different scenes are taken from the same kind of distribution or same kind of scenes, that like you're exploiting the similarity for better generalization, so that then you need less context images to be able to perform reasonably well, because you're sharing information across all those things. So that's not too surprising, but it's very interesting from the like the comparison with NeRF is I mean, it's interesting, but it's something that you would expect. The comparison with like a normal VAE is very interesting. They have many experiments that I'm not gonna go into here, but one interesting experiment here is like where they give this NeRF-VAE a context image, which has only like you can see the object, but only a little bit peripherally, right? And and it, based only on this, is able to reconstruct a full new image. Or I guess this one in other images, but is able to reconstruct something like the real object. And so here, this was the ground truth from a different. So this one, none of the images, I guess, that were given as a context showed the object in like full view, right? And this ground truth, but the model never seen this. But the model is nevertheless able to predict it, or to do fairly well at reconstructing it, because it has this like geometric prior. It's not just trying like the normal VAE would do to make something similar, or to generate images that are similar. Because it doesn't have that prior, here the only way that you can justify when you reconstruct this thing, where you try to reconstruct this, the fact that there's like a little bit of an object here, it has to create an actual 3D model of the object. So the only way you can do that is by having a real object there, and that means when you're gonna change the view, you're gonna see that object, which is pretty interesting, and I think is very interesting to look at integrating much more of these like kind of geometric priors, or geometric things that we already know about how things in perspective work, or how to render like images given like a 3D model, so that the neural network part is like in building the 3D model and not in building the images straight up. So there's less kind of a burden on the neural network. So this overall was a very interesting paper. I think is a very interesting direction in integrating this like geometric awareness in VAE. And yeah,